Hello all, welcome to part 9 of the Buffer Overflow Primer video series. In this video, we will look at a demonstration of the return to Libc exploit. So let's bring up our terminal. Before we actually begin with the programming aspects, what we need to understand is that probably there are already various stack protections applied to the kernel which we might be using. Let's quickly look at the kernel version, and if you notice, it is a 2.6 kernel. So if you remember in the slides, there were various protections which we spoke about. We had NX non-executable memory and ASLR, etc. So on this kernel, non-executable memory patch is applied, and so is ASLR. For this video, let's go ahead and disable the ASLR protection. We will cover how to combat ASLR in a separate video. So just to confirm that ASLR is indeed enabled, let's look at the process memory map. So we are looking at our own process memory map, and if you notice in this invocation, the stack basically starts at BF81C000. Now if we once again invoke the program, you will notice that the stack location has changed to BFB7C000, right? And this is what reflects the fact that the various segments have been relocated. And what this means is that address space layout randomization is currently enabled in the kernel. Now there's a very simple way to disable it, and that is using the procsys kernel randomize VA space. So we just echo 0 into it, write 0 into this variable. And now when we actually look at our map, if you notice, BFFEB000 is where the stack is located. We invoke the program again, and if you notice, the stack location has not changed. In a separate video, we will look at how to combat ASLR. In this video, we will just look at how to go about combating the non-executable stack problem. So let's bring up our victim exploit.me.c. This is exactly the program which was there in the previous video. I've just added a get char statement, and I'll tell you why a little later in the video. That is the only modification which has been made. Let me compile this program. Now let's go ahead and open up our other program, which is actually going to be the hacker program. So this is the program read to libc.c. And what we've done is, if we go back to our slides, basically we have gone ahead and created an environment variable once again, which will go ahead and create all of these program structure. So before we do that, if you remember, we talked about finding out the address where system, exit, etc. are located. So the way to do that is basically, let's quit the program. Let's load up exploit me in GDB. And let's go ahead and break in main, run the program with a demo input, simply hi. So the way to figure out where the system libc call is located is simply to go ahead and print that on the screen. So this is where the system call is located. Let's actually open up thread to libc.c And if you notice, this address in reverse order 60 BE, AE, and B7 is what we have written here, right? 60 E5 EA B7, 60 E5 EA B7. Similarly, the exit call is located at this address, right? And we've copied that here. However, currently we do not know where the string /bin/bash is. If we go back to our slides, this was the third thing which we require. Now what we are going to do is go ahead and inject this string as an environment variable. We'll look at how we'll do that a bit later. So now just following the program flow, we had 80 bytes of the buffer variable, 4 bytes of the frame pointer, 4 bytes of the return address, 4 bytes of what is going to be stored as PTR2, and then the final 4 bytes of PTR3. So this in totality comes to 96 bytes. Along with that, we are going to have a 4-byte padding for the null and a 4-byte pre-padding to name the environment variable. So all this together comes to 96 plus 8, 104 bytes. Now let's go ahead and actually fill up this entire buffer with nopes, even though it doesn't really matter, but still. And then in the beginning of the buffer, we name the environment variable, which is buff. From there on, we stored buff here. Then we straight away go to 84 plus 4, 88, 80 plus 4, 84, and 4 bytes for buff is equal to, which comes to 88 bytes. And this is the place where we go ahead and store the address to the system libc call, right? This is where we store it. Then at 92, we go ahead and store the exit libc call address. And then finally, at 96, we go ahead and store the address to the bash bin/bash string. And then finally, we just have a 4-byte null padding. Then we put this variable into the environment and then call bin/bash. Right now, we have not filled up the address to bash. We'll do that a bit later. So let's compile this program as well. Now what we shall do is, in order to find where bash needs to be located, the first thing we will do is run the return to libc program. As expected, we get a bash shell with the environment variable buff set to an appropriate value. Now we go ahead and inject the bin/bash variable. So let's actually inject bin/ the k shell or the con shell. Right. Now we need to know in some approximate way where this would be located in the program memory. So for that, what we have done is written a very simple program called get environment variable address.c. What this simply does is it goes ahead and uses get environment variable. You pass the name and it actually tells you the address, right? This would be a good starting point. There would be some minor differences in every program's memory location where the bin/ksh would be mapped, and we would look at that a bit later. So let's compile this program. And now go ahead and give it the input, which is my shell, so that we get some approximate address. So this is the approximate address where the bin/ksh string is present, right? Now the next thing which we are going to do is go ahead and run the victim program, which is exploit me, and give it the input, which would be buffer, right? So if you remember, we have a get char, and that is where the program execution is currently waiting. Now, in order to look at the memory space of this program, let us attach GDB to this instance of exploit me. Let's go to the other terminal. First, let's figure out the process ID of exploit me, which is running in the other terminal. So if you notice, 3150 is the process ID of exploit me. You can see this whole string of garbage here. That is the $buff which was passed to it. So now let's fire up GDB and let's quickly go ahead and attach to process 3150. Now what we shall do is go ahead and figure out where exactly the bin/ksh variable has been stored. So we have an approximate address value. Let's examine that. So if you notice, bin/ksh is not located here. Let's actually press a couple of enters. And what we will notice is bin/ksh is actually here. So let's find out the exact address. We know it's 48. This would actually mean 50. So this is the address where bin/ksh is mapped in the exploit me.c program when it is in memory. So now let us go back, continue the program execution, exit from both these shells, and go back to our return to libc.c program and go ahead and enter this address for bash. So this is the bin/ksh location. So it is 50fd. And then we have ff and bf. Let's recompile the program. And now let's go ahead and run it again. So the program is running. We are inside the bash shell. Now let's go ahead and once again set up the my shell environment variable consisting of bin/ksh. Right. So now basically the buff variable is there and the my shell variable, both have been set into the environment. Now let's run exploit me with the buff as input. So basically now the return address etc. has been set properly. The bash string location has also been set. So now when we execute this is the get char. Here we are. So we are into bin/ksh. It has been executed and we now have a shell. Let's exit this. So well, that was it for this video. Basically what we've done is we've subverted the NX protection, which stops from executing instructions from the stack. So we use the return to libc exploit strategy in which we went ahead and actually had code executed from the libc library, which is memory mapped into the process. And that is how we were able to get our shell. Hope you enjoyed this video. I would encourage you to actually download the code and try out these examples on your own computer. I would also love to hear all your feedback. Please leave your comments behind. Well, that's all for this video. Thank you.